Hello there, Martin and possibly Larry, and welcome to my oral maths assignment. This assignment was a two-part assignment, and therefore it's going to be a two-part presentation. The first part is going to be a presentation of a project which I myself have worked on, and the second part is going to be a presentation of a mathematical proof that I've chosen, and we'll get to that later. Now, the first part of the presentation is going to be on a screencast because I felt that way was the easiest way to present it to you. And the second part is actually going to be a recording of me standing and presenting it. So, without further ado, let's just get into the first part. Now, A. Present a project which you have made in your 3 years on Sogatome. So the project that I've chosen to go with is a project that we made under the mathematical subject of differential equations. What is a differential equation? Well, the term itself is fairly simple to explain. It's simply an equation in which a joint of differentiation exists. So differentiation is the second part of calculus, which determines the inclination or declination of a point in a function. This type of calculus can be used to a wide variety of fields, or in a wide variety of fields, sorry. It can be used to determine highs and lows of a function, which in turn can be used to optimize different things. For example, you could use it to determine the smallest possible radius for a container with a set volume, so that it would be constructed with the smallest amount of resources and thereby saving money and materials in the process. Another example would be a speed time graph. So if you, for example, monitored the distance a car moved over a given time interval, the inclination of the function would obviously dictate the speed that it was moving with. And if you were wanting to know what speed it was moving with at a certain time, you would then differentiate the function in relation to that time, and you would get the specific speed. Simple as that. So, the project itself were based around water watches, and what we were to do was choose two different shapes which would resemble our watches, and we were then to compare how the shape of the watch influenced the time it took to empty the container. And why water watches is something we'll go into right now. So, for as long as there's been people on this earth, some form of necessity to keep track of time has existed. The first primitive watches that was created by man, obviously, were solar watches, and these used the sun's placement in the sky. They did this by shining a light through a hole, which would in turn cast a beam on the ground or some other material, and you could then use that as an indicator to tell what time it was. The issue with this, however, is that it would obviously only work when the sun stood high in the sky. So at night, it was absolutely useless, and one can imagine that it would be rather useless when it was cloudy. So in winter months, it must have been a hell to use because it's always cloudy because of rain or snow, and the sun sets quickly. So the water watch was the solar watch's successor, and the principle behind a water watch is fairly simple. You have a container with water in it, and the time it takes to empty the container from a hole in the bottom will dictate what time it was. You will use to tell what time it was. So markings would be made on the inside of the watch, so that you could quickly use the water level to tell what time it was. However, one thing to consider, one thing to keep in mind is that the water would not always flow with the same constant speed. If you, for example, had a cylindrical shape with a simple hole in the bottom, the water would flow significantly faster at the top than it would at the bottom. This is obviously due to the fact that there's more mass at the top or at the start than there is at the beginning, but at the end, sorry. And gravitational pull obviously works more or is more effective the more mass there is. So to put this in perspective, if one were to divide a container, a cylindrical container, into a set number of minutes, then the intervals at the top of the cylindrical container would be larger than the interval at the bottom, because it takes less time to get from point A to point B than it does to get from point B to point C, or from C to D. Now, this is expressed by something called Torricelli's law. It expresses that the outflow speed, called Q, in for example the unit liters per minute, is dependent on the current water level above the outflow hole. And the formula is what we see right here. It's Q equals K times the square root of H, where K is a constant determined by the properties of the hole, so the shape of it and the size of it and stuff like that, and H is in turn the water level above the hole. Now let's go into our project. So the shapes that we chose to work with were a cube and a cone, and we would have originally liked to work with a cone and a hemisphere, but we ran into some calculation errors that no one seemed to be able to surpass, so we substituted the hemisphere for a cube. And some properties were determined beforehand. For example, we knew that the volume must be equivalent to 10,000 cubic centimeters and that K must be equivalent to A. So, in order to keep this simple and easily understandable, I will only delve into the first part of that assignment, namely part A. So, in part A, we were to make a differential equation called dH over dt by considering the change in volume in a small time interval. Here we would have a cross-sectional area called A, which is dependent on H as well. So what we've done is we've constructed our equation with the knowledge that the change in volume over time must be expressed by dV equals Q times dt, where Q is the speed at which the volume decreases over time, namely dV over dt. So since we are working with small time intervals, the difference in water height must be equally small. Thus, dV can be seen as a formed cylinder, even though the watch itself is another shape. And this is a principle commonly used in integration. In our case, we would divide our shape or our watch into an infinite amount of discs, and then we would add them all up. So the difference in volume can then be calculated as the volume of a prism, so the bottom area multiplied with the height. And that's exactly what we see here. So what we can do now is equate our equations so that we get this expression. What we do then is isolate what we are interested in, so dH over dt, and we would end up with this expression. And because Q is a part of this, and we remember that Q is from Torricelli's law, we can then extract Q from Torricelli's law and insert it, in turn leaving us with dH over dt is equal to negative K times the square root of H over A of H. And this is the differential equation that we're searching for, and that's the answer to part A of the assignment. And this is the equation that we're going to be working with for the rest of the project. So what I've done is I've taken the graphs of our two shapes and I've plotted them here. And what we see is that there is a huge difference in time. So there's a huge difference in the time it takes to empty the container. For instance, one of them almost empties at, what can we say, 250 or 260, 70 minutes, and the other one empties at roughly 500 minutes. That's almost twice as much. And this is even though both of the shapes have got the same K value, so the same shape in the outflowing hole, and the same exact volume, we are then able to see a significant difference in the time it takes to empty them. One of them starts off, this one, almost linear, and then it suddenly drops out of nowhere. Whereas the other is exponential and almost goes infinitely slow at the bottom. So what we're able to conclude at the end of our project, and the conclusion of this entire project, is we can conclude that the shape of the watch plays a significant role in the time it takes to empty it, and that this can be foreseen or calculated by differential equations. So yeah, that's basically the entire project. So, well, scratch down to roughly 7 or 8 minutes. And what we're going to be doing now is we are going to move on to part B of the presentation, and I'm going to be doing that in person. So you will have to do with Future Shamim from now. So I'll see you in a second. Hello again, and welcome to the second part of my presentation. So as I explained before, the second part of this presentation is going to be a presentation of a mathematical proof which I have chosen myself. And the proof that I'm going to be presenting is the proof that integration is related to area under curve. And yes, we're just going to go right into it. So what I've drawn out here is a function. It's a random function, and what we see is that we've got a point x, and what we're interested in figuring out here is the area up till x. Now we're going to express this with a simple function simply called a of x. So this in here is a of x. If we then are to go a reasonably small amount out further, and we go out h further, then we're going to have a point x plus h, and the area is going to be a of x plus h. That's what this function means. It's simply going out the x-axis and taking the area up to that point. Now, if we are to look at this area in here, there are two ways to do it. The first way to do it is simply go out and say, well, we go all the way out till x plus h, and then we extract or minus the area up till x from it. So we would do that simply by writing a of x plus h minus a of x, and that would be this area in here. Now if we however are to look at it as a rectangle, or sort of a rectangle almost, and we then draw it out here, we see that it's a rectangle almost with the width h, and as soon as we cut it off here, then it's a rectangle, perfect rectangle, with the height called the y value of the f of x, the y value to x. So this point right here is going to be f of x, and this height is therefore going to be called f of x. So what we see is that because there's still a part sticking out, we know that the area, the total area, must be greater than or equal to f of x times h, because it's a simple rectangle. Now, if we however go all the way up till here, we then see that the new height is going to be the y value of x plus h. So it's going to be f of x plus h. And the height is now changed, obviously, till f of x plus h. So it's then going to be less than or equal to f of x plus h times h. Now, because this is a basic inequality, what we can do is just do whatever we want really, and what I'm going to do is I'm going to divide it through by h. So what we do is we divide each and every joint of it, and the first is going to look like f of x, because h and h go out with each other. The second part I'm just going to write out because it's way too complicated to actually divide it through. So it's going to be looking like this. And the last part is going to be f of x plus h, well, times h divided by h, so just f of x plus h. Now, what we're allowed to do is, or what I'm wanting to do, is take the limit of h tends to 0. Why? It's not something I'm going to delve into, it's just something or whether we can that or not is not something I'm going to delve into. It's just, you've got to accept that I'm doing it because it seems to be perfectly capable as long as h is a positive number, so that we don't divide through by 0. Now, what we're going to do is we're going to take the limit of h tends to 0. And for the middle part, again, I'm just going to write it. So h tends to 0 of a of x plus h minus a of x over h. And when we take the limit of something towards 0, tends to 0, then we are talking about very small values of that variable. In sense, we just substitute it with 0 and then we calculate it. So that's exactly what I'm going to do. Now, because h doesn't it's not included in this part of the expression, it's gonna remain the same. However, over here we see that h actually includes, so it's gonna be f of x plus h tends to 0, which is just substituting it with 0. So x plus nothing, which in turn is just f of x. Now, this part in here we know to be the first derivative of a of x, and we know this from the other part of calculus called differentiation, which I went over in the first part of my project. So this, because it's the first derivative of a of x, we can substitute it with the expression dA, so the difference in area over the difference in x value. We then write out everything else just as such. And the first thing we notice then is that f of x are on both sides of dA dx. That means that dA dx has to be bigger than or equal to, and at the same time it has to be less than or equal to f of x. This is, if we apply what we know as the squeeze theorem, we then see that if something are to be greater than and less than or equal to at the same time, it's the same as saying that it's equal to. So if d of dA dx are to be equal to f of x, then we must simply be able to write it out as dA over dx is equal to f of x. And now we've got a function, and if we are then to integrate this function, we will end up with something looking a bit like this. So if we integrate f of x in relation to x, we then get the area in relation to x. And this is the proof that integration is related to area under curve. And that's the filled up square. Now, one might ask why this is necessary, or why you would ever want to use this, but integration under a curve is used in many fields. For example, in physics, if we have a function looking a bit like this, and we've got something like distance traveled over time, and we have a function looking like this, something like that. No, it's supposed to be speed over time, and we monitor that, and we then integrate it in relation to time to a specific point, so from 0 till x. We then get this in here, which would tell us how far the object has traveled. And yeah, that's gonna wrap up my presentation of my proof. Hope you enjoyed it, and I hope it made sense, because it did to me. So yeah, thank you. I'll see you.